always, brain research. We'll see today Big Bang cosmology and Penrose tiling. Some of you might not be so familiar with that. It's not the topic of the talk today. I think it's very fascinating. You take two geometrical objects and you put them together in a very delicate way, maybe Roger can comment on, such that the pattern is never periodic. And that's why Penrose tiling is used for quartz crystals. We can go into magnify this one. You see here, get fantastic panel. It's not periodic in any direction. And I think this is used in various panels on floors and on walls and things like this. So, I think at technical university, isn't it true? Maybe not. But, so, it's a great pleasure for us to have you here, Roger, and I see a lot of young people interested in science. Please, let's welcome.
I think I'm not switched on. I hope you can hear me at the back. Good, thank you. No, it's a great pleasure always for me to get back to Copenhagen, meet old friends and see the wonderful city, which we appreciate greatly. And it's always relaxing too, that's the great thing about Copenhagen. I'm afraid my talk has nothing whatsoever to do with that. It's nice to see the picture. No, it will be about this, which is a space-time picture of the universe. Starting from the Big Bang, time up the picture, so my diagrams will be of that character, time moving upwards, so as time progresses, the universe gets bigger. You'll see this stuff at the back is just to indicate that I don't want to prejudice the issue as to whether the universe is spatially closed or continues indefinitely to infinity. So my pictures are to be unbiased with regard to that. As far as I can make out, it doesn't matter in what I want to say whether the universe is finite or infinite spatially. However, we do have this Big Bang, we do have the universe expanding, and then we do appear to have an exponential expansion, so it's accelerating, the expansion is accelerating, and we're somewhere in the middle here where you're just beginning to notice this exponential expansion. It's crucial to what I want to say that that is present. There's also something mentioned at the bottom here, which is inflation. Standard cosmology these days requires that there was also an exponential expansion which took place right near the beginning. It's not marked on this transparency for two reasons. One is that it would not be visible on this scale at all, it would be right up in there. And the other reason is that I don't really believe it. The scheme that I want to describe is in a certain respect an alternative to inflation. And I'll try and explain in what way it is. So since I have two projectors, I can exercise myself along the way over here. I hope you can see both slides. You see at the beginning there, we have this thing called a singularity, which is where the geometry of space-time goes crazy. According to Einstein's equations, we will find that there is, the densities become infinite and everything goes wrong and the equations give up. The other place we have singularities is in black holes. Here we have the collapse of a black hole, and again time is going out of the picture. We have some star or some other body or collection of bodies which is collapsing inwards, and these things are the light cones here. If you have a light signal, this shows you how that light signal will propagate into the future. So as time progresses, the speed of light is represented by this cone. Material particles have to travels less than the speed of light, so that they would have world lines, that is, histories which are within the cones. And here, the thing about the black hole is that the cones tilt over as you get nearer and nearer to the center, and the cones become vertical in the picture, so that the light and no other particles can escape. Once you get stuck in here, you can't get away because you have to cross this cone in an illegal direction, which would not be within the cone. Material bodies, as here, you see the matter has to travel within the cone. In the middle we have the singularity, which is another place where curvatures go to infinity. And people in the old days used to compare these things. These two types of singularities were considered to be one the time reverse of the other, in a sense. Well, if we have black holes, then we have to modify this picture here with the singularities, which are now drawn, indicated they will come about at various stages, and they represent, in a sense, the end of time. If you happen to fall into a black hole, you are guided into that nasty singularity, and there is no escape. So that would represent your future singularity, and this would be your past singularity. So that's the sort of picture that we have of the universe. Now I want to say there are things more about that. One is, this is a sort of issue that, see, one of the reasons people introduced inflation was that they wanted to explain that the universe, why it was so regular and smooth and things like that. And I just want to indicate why inflation doesn't do it, even though I haven't really told you what inflation is. But let's consider what would have happened if you had a collapsing universe. You see, the important thing that I'm going to address here first is a thing called the second law of thermodynamics, which, roughly speaking, tells you that things get more random as time goes on. I'm sure I'm talking to physicists here, but I may be talking to people who are not physicists, so I'll say a few things which are very familiar to people, but rather fast. Don't know whether that helps much, but here we have what would happen if you have a collapsing universe, which is, of course, if it was exactly like this, you wouldn't see any difference, except the time would be going the other way. And since the laws which are involved are all reversible in time, if this is an allowable universe, then so is this one. But if you consider that you have, the thing looks overall similar to what it did here, but going the other way in time, and you introduce little tiny irregularities in the detailed motions of particles, then these would build up in accordance with the second law of thermodynamics, and you would find irregularities collapsing, and you would ultimately get black holes, and these black holes would congeal, and you would have a great mess at the end. And the thing that's rather peculiar about the Big Bang is that it wasn't like that at the beginning, that we had a very special state at the beginning. And I want to say something about that. First of all, the issue is, why do we believe in the Big Bang anyway? And one of the most important reasons for believing in the Big Bang is the existence of this microwave background, which is light in all directions. When I say light, and it's electromagnetic radiation. It's at a much, well, here we have the spectrum here. You have, this is the frequency of the radiation going this way, and this is the intensity going this way. And it's at a temperature which is about 2.7 degrees above absolute zero. So it's very, very cold. It's often referred to as the flash of the Big Bang, cooled down through the expansion of the universe. It's not actually the Big Bang itself you're looking at, something like 300,000 years after the Big Bang, but nevertheless it's pretty early. And what I want to show you here is that this curve here is a famous curve, which is what Max Planck was able to demonstrate with the consequence of his idea that energy comes in little bundles. E equals h nu, the famous formula, nu being the frequency, h Planck's constant, e the energy, so the energy is always in proportion to the frequency. And using that, he was able to show that if you have matter and radiation in thermal equilibrium, so you have this container and you let it settle down into equilibrium, then you always find that the frequency has this particular spectrum. Now here we have the curve is the exact Max Planck curve, but we have little error bars going up here, but these are exaggerated by a factor of about 500. So if I squash the error bars down, those are the observations, if you like, are that far off, you squash them down, you find they hug the curve to within the thickness of the ink of the curve. So it's an extremely precise illustration of the Planck curve. What does that tell you? That tells you that what you're looking at is basically something in thermal equilibrium, which is another way of putting that, maximum entropy, another way of putting that, is to say maximum randomness. In other words, what you're looking at, and here's a paradox, so it seems, what you're looking at is something where the state of the universe seems to have been as completely as random as it could be, and according to the second law of thermodynamics, this randomness will be increasing. And so, how does it increase when it's got nowhere to go? It's already at its maximum. You might say, well, the universe is expanding, so there's more room for something or other. That's just not the right explanation. It doesn't make sense because of this reversing argument. You say, okay, whatever it was doing here, you let the entropy increase, the randomness increase, and you get this collection congealing of black holes. And the puzzle is why you didn't see the universe like that to begin with. And so there is a profound puzzle to do with cosmology. Just to illustrate what that's about. Here we have second law illustrated, a gas in a box. If you initially started off right in one corner and release compartments there, then the gas will spread out over the box. And this will be entropy increasing or randomness increasing. Time goes on. And that's certainly what you would expect for a gas in a box. So if it was just the matter running around, then you would have something which is very uniform. Let me mention, I should say, two things about the microwave background. One is the fact that you have this curve, which indicates that as far as the radiation you're seeing is concerned, it looks like maximum entropy or maximum randomness. But you also see over the sky as a whole something which is very, very uniform. And if you correct for the Earth's motion, which gives you a slightly more higher temperature in the direction we're moving and a slightly lower temperature in the direction we're moving away from, if you correct for that, you find that the temperature over the whole sky is extremely precisely uniform to about a few parts in 10 to the power 5, 10 to the power 5, so 10 to the a few parts in 10,000. So that's the sort of precision that you have in the sky. And that's consistent with this picture because you see the high entropy or random state, as far as the particles and the radiation is concerned, is indeed uniform. But it's low entropy or low randomness with regard to gravity, because you would expect if now we'll imagine this isn't a gas in a box, but a whole lot of stars in an absolutely huge galactic scale box, then these things will start to clump and get more and more clump until they finally form black holes. And the entropy is going up all the time this way. And what we appear to see is not this very high entropy situation, as I indicated in this diagram here. But what we appear to find is something like that. And that is very strange. And I'm always puzzled by why cosmologists are not more puzzled by it. It seems to me very strange and that you have very high entropy for everything except gravity, and very low entropy with regard to gravity. So imbalance, and the gravitational force, if you like, is treated completely differently from everything else. You have a combination of those two situations. In the very early universe, or as Lee Smolin has recently described it, you roughly speaking have two completely different temperatures. In the early universe, you have a very high temperature from the matter and a very low temperature from the gravitational degree of freedom. And that is something which needs explaining. So I've worried about that for many decades, and another way of putting the issue here is that you have a fundamental problem raised by the second law of thermodynamics and the nature of the Big Bang. Why did the Big Bang not involve any white holes? You say white hole is the time reverse of a black hole, so when I show this picture here, that's a lot of time reverse black holes congealing, or bifurcating as time goes on. And that's not what we see. What we see is that. So the question is, why? Fundamental question. Why did the Big Bang not involve any white holes? That's time reverse black holes. And this is not answered by inflation or by any other current theory of quantum gravity. People tend to think that to explain the situations where you have infinite curvatures according to Einstein's classical